Right, so let's consider now what happens when the energy is positive. In that case, the orbit is going to be hyperbolic. The hyperbolic orbit is this orbit here. The green has an eccentricity that is bigger than 1. So as you increase the energy at constant angular momentum, you pass from an orbit that is a circle to an ellipse to a parabola and then to a hyperbola. And the hyperbolic orbit is interesting also because it's essentially what happens when you have a gravitational deflection. When the bodies are not in orbit, but they're passing each other with enough kinetic energy that they do not become bound, but they are deflected. It's essentially the trajectories that we send spacecrafts in the solar system to an encounter with a planet that is a flyby and not an orbiter mission. So from the geometry here, you can see that you can follow the trajectory of the spacecraft, essentially following hyperbolic orbit. And you can know the deflection based on the impact parameter of the encounter. The properties of the hyperbola are readily seen here from first the definition of the eccentricity. You see here from this that if you have positive energy, then the eccentricity is bigger than 1. And the equation you can use from the equation of the ellipse. And because the eccentricity is bigger than 1, you flip the sign of the second term so that geometrically you still have a positive term. So mathematically, that is the equation of a hyperbola. Now geometrically, the semi-major axis is the distance from the center to the point of perihelion. The eccentricity is A times E is this distance in here from the center to the focus. You can see here that Q is A times square root of E squared minus 1. Now, because the energy is positive, the semi-major axis now cannot be defined as the negative of the energy. It is redefined as the positive of the energy. Semi-major axis is mu over 2E. And similarly, the semilatus rectum is redefined also as a positive quantity. Now it's P equal to A E squared minus 1. So summarizing, we can construct this table here for the geometrical and physical properties of the orbits. You have for the circle and the ellipse, the bound orbits. For the circle, the eccentricity is 0. The semi-latus rectum is equal to the semi-major axis, and the energy is equal to the minimum energy. For the ellipse, you have that the eccentricity is between 0 and 1. The semi-latus rectum is A times 1 minus E squared, and the energy is between the minimum energy and 0. For bound orbits, the parabola and the hyperbola, for the parabola, the eccentricity is equal to 1. The semilatus rectum is equal to 2Q, Q being the perihelion distance, and the energy is equal to 0. For the hyperbola, the eccentricity is bigger than 1. The semilatus rectum is A times E squared minus 1, and the energy is bigger than 0.